Okay. Whoa, what are we doing? We're going to move on to a new unit. Hopefully it's unsurprising that I did not have time to mark your exams last night because it was parent-teacher interviews and I was here until 7:30. And then I had to go home and do a bunch of stuff, so not happening. They'll get marked tomorrow, maybe. Check Power School, I don't know. You'll get it when you get it. You'll get it back when you get it back. If you haven't written the exam, you got to write it as soon as possible, basically. So, you know, whatever. Hey, I got a thought experiment for you. Imagine that you are imagine that you're this person. Here you are. You're an astronaut. You're floating in space. But actually imagine that you're not even floating near the Earth, right? You're just an astronaut floating in space, okay? So you're sitting there. You're stationary. You want to go that way because that's where the International Space Station is, or that's where your spaceship is. You know what I mean? So, like, how do you do that? How do you get that way? Do you swim? Can you swim? No. No. So how does swimming work? If you were actually in a swimming pool, why does you doing this, why does that make you go that way? Ooh, because you're pushing water that way, which causes you to go that way, right? So if there was no water or no air, and if you were just floating in an empty swimming pool in space, right, could you swim your way over to your spaceship? Shucks, huh? Oh, well. So what do you got to do? What's the only thing you can do?
Ask for help.
Ask for help. Say, Houston. Yeah, we got a problem. So, okay. Is there anything you can do?
What do I have on me?
What has to happen? So, okay, you radio for help, but how are they going to get you over there? Like, what does something else have to do? What?
A grappling hook.
A grappling hook. Nice. Okay. So they fire a grappling hook by you, near you, something like that. Basically a rope, right? They send a rope your way, and then you take the rope. Okay, so you're out in space, you're floating in space, you want to go that way, and what do you have to do with the rope?
Pull it.
Oh, so you got to pull onto the rope, and as you pull onto the rope, you're going to go that way. What are you doing? By pulling on the rope, you're applying a force. So you're stationary out in space. What is the velocity of somebody who's stationary? 0. And then, but you want to start moving. You want to have a velocity, right? So does your velocity have to change? What's the only way that you can change your velocity? You want to go from 0 to positive something, +1, +2 meters per second. What's the only way you can change your velocity out in space? Yeah, by pulling on the rope. You have to apply a force, or somebody else has to apply a force. Would you agree that you could just tie the tether to you, I don't know, like clamp it on a part of your spacesuit, and then you could just sit there, and as long as somebody else pulls you, you're still good to go, right? Okay, so what do we have to do? We have to apply a force. So this is kind of the first major conclusion that we have to come to here. So it's the definition of what a force is. A force is a push or a pull on an object. How do we measure, how do we measure distances? Well, we measure distance with some sort of a ruler, right? Would you agree the ruler can be small or it can be big? We can measure distances in different units. What are some units that we can measure distance in? What's a unit of measurement for distance? Meters? Kilometers? centimeters,
Feet.
millimeters. Could you use desks?
Yeah.
The classroom is 20 desks wide. Is that, as long as a desk was a standard length, right? As long as each desk was a standard length, yeah, you absolutely could, right? So okay, but what do we measure force in? Not joules.
No, that's not.
Somebody said it. 3 people said it. Newtons.
Yes.
I said it.
Yeah, I said 3 people said it, but we measure forces with a spring scale. Most of the time. Have you ever seen a spring scale before?
Oh, I think I know what you're talking about.
There we go. No, that's not what I want. Here. So here's a spring scale, right? And so we could take somebody's, for example, backpack. Ooh, that's a nice weight, okay? So I could take Josh's backpack, I just stole it, right? And is the backpack, when I let it go, is the backpack going to apply force onto the spring scale?
Yeah.
Yes, and we can measure the force, right? The spring scale should move a little bit. And so what is it measuring? 26 newtons or something like that? Okay, good, perfect, right? So absolutely forces are measured using a spring scale traditionally. And we measure them in newtons. In units of newtons, or N. There's a pretty famous equation when we talk about forces. I don't know if anybody knows the equation when we're talking about forces. F equals, that's okay. So F net equals mass times acceleration. We're going to talk about net force. Right now, all we care about is just one force right now. So whatever. The net force on an object is if there's only one force, it is that single force, okay? You have this kind of on your data booklet or on your formula sheet. Now, this was an equation that Sir Isaac Newton made up. But it's not the way he wrote it. The way he wrote it when he first came up with this idea of force was he wrote it as this: the acceleration of an object is equal to the net force applied on the object divided by the mass. So if you want to know what the acceleration of an object should be, then you need to know the force you need to apply and the mass of that object. That's the way he initially thought of it. So this is the way it's reported in your formula sheet. Can you understand how we can get F net equals mass times acceleration from this? Right, okay, good. So we're just rearranging for F net. That's all we're doing. Good. So let's see what a Newton actually is. So let's toss the number 1 in here for everything. So if I had 1, what's mass supposed to be measured in? Kilograms. Good. That's the IUPAC unit for mass. So 1 kilogram times 1, what's acceleration supposed to be measured in? Meters per second squared. Okay. So what are we going to get? Well, what's 1 times 1? 1. Good. And then kilogram times meters divided by second squared is kilogram times meters divided by second squared. Can you understand how I could have written everything over the second squared if I wanted to? It doesn't make a difference, right? Either divide this or divide the whole thing. It's the same thing. So that is this unit right here. That's a Newton. A Newton is a complex unit. It's made up of other standard units, kilograms, meters, and seconds. You have to know what a Newton is in its fundamental units. So can you understand, though, how or why we would shorten this humongous unit, right, kilogram meter per second squared, into a Newton? Because physicists, and just like chemists, are inherently lazy, and we want to try and shorten things as much as we humanly can. Okay, good. So there's lots of forces that could act on an object. There are many types of forces that could act on an object. For example, I'm going to show you an example of what I'm talking about. I'm going to take this hole puncher, right, and I'm going to try and accelerate it. So, okay, in order for me to accelerate it, in order for me to change its velocity, what do I have to do to it? I got to push it or pull it. Okay, so I'm going to pull it. Okay, so here we are, 3, 2, 1. Whoa, did I just change its velocity? Holy cow, crazy. Let's draw a diagram of what's going on there. We're going to simplify this picture of a hole puncher, and we're going to draw it as a box. Because physicists traditionally are not amazing artists, so we try and simplify things as much as we possibly can. So what are all of the forces that are acting on that object? Like, okay, obviously I was pulling it, right? So, okay, so I should probably pull it. So I'm going to draw an arrow kind of going out of the box. This is not a traditional, what we call free body diagram, but that's fine. So I'm pulling it. We always draw forces as a pull, as something not, we don't draw forces as going into an object. We always draw them as going away from an object. So yeah, I was pulling it, sure. But even if I was pushing it like this, right, same thing, we would still draw the force like that. That's what we call an applied force. So it's not applied, it's an applied force. F applied. I'm applying a force on it. Are there any other forces acting on this object right now?
Gravity.
Ooh, is gravity acting on this object? Whoa, gravity's totally acting on this object. What are we going to call that? We're going to call it F. Nope. FG. FG is force of gravity. Or force due to gravity, but force of gravity. Does every object have the same force of gravity? Like if you took Mr. Walton's force of gravity, if you took how hard gravity is pulling on me, and then you took how hard gravity is pulling on the hole puncher, are they the same force, or are they different forces?
It's about the same. They're different.
If you put Mr. Walton, and if you put the hole puncher, if you put us on a seesaw, you know what a seesaw is, or a teeter-totter, whatever? Okay, so if you put us on a teeter-totter or a seesaw, would we be balanced on the seesaw or the teeter-totter? No. Who would win the battle? Mr. Walton will, right? So gravitational forces are not the same. Okay? Acceleration due to gravity is the same, but gravitational forces are not the same. Okay, well, if these, okay, look at this diagram. If these were the only two forces acting on this object, where would it accelerate? In what direction would it accelerate in? Would it accelerate in that to the right? No, it would accelerate like this. Because there's a force going this way, and there's a force going that way. Did it accelerate through the bench top down into the ground? No, it didn't. Okay, so clearly there's some forces that we're missing here. There's some forces that we're missing. Yeah.
This feels like a stretch, but Isn't the desk pushing against it upwards as well?
Come on, let's go! Woo! Did you hear that?
Yeah.
Is the bench top applying a force on this thing?
Yeah.
Yeah, otherwise it would fall through the bench top, right? Absolutely, this thing is applying a force on that thing. So, how am I going to draw that, Brennan? Where should I draw an arrow?
An arrow going up from the top.
An arrow going up. And it should be, I don't know if you know this, but how long should I draw it?
I think that's good.
It should be exactly equal to this thing. Because is this thing accelerating up or down right now? No. So the force this way is equal to the force that way. They're totally balancing each other out. So I should go like this. Do you know what that's called? Nobody's going to get this. But we call this Fn. It's called the normal force. Normal is not a word that is used in the scientific community quite regularly.
Quite normally.
Yeah. So, okay, whatever, that's fine. Okay, was there anything else? Were there any other forces acting on this thing? Kind of. We're going to ignore air resistance because was it moving fast enough for it to really get slowed down by the air? No, but there was another force acting on this thing. What was the other force acting on this thing? It was something dragging it backwards, Hunter? Friction. This thing and this thing, right? Here, I'm going to push it, but then I'm going to let go, and we're going to see what happens to it, right? Ready? 3, 2, 1. Okay. Well, I accelerated it, but then I let go. If there was no friction, what should have happened to it? Just kept going. It's a lot like if you were out in space, if you're this astronaut out in space, right? Imagine this astronaut had a little ball beside him or her, whatever. So if they push on this ball, would you agree the ball's going to accelerate? As long as they're pushing on it, it's going to speed up, right? But as soon as they let go, is it going to continue to speed up? No. So they push on it, the ball's going to go, damn it. They push on it. Okay, the ball's going to accelerate, but then it's going to move at a constant speed. Is this ball ever going to slow down?
No.
Not until it
It's something else.
hits something else or another force is applied to it, right? The only way you can change the velocity of this object is if a force is being applied on it. So when I push this thing, would you agree while I push it, it's going to speed up, right? But then when I let go, it's going to slow down. Clearly it's slowing down because there's another force acting on it. That is the force of friction. So we say FF. And this is the force of friction. Are the skateboarders going to be distracting? No?
It's fine.
Okay. Let me know if I should close the windows because I thought it was getting hot in here. Do you think it's hot in here? Yeah, I don't know what's going on with the AC, but I haven't touched it. There's tape over it. Nobody's touched it. But I feel like it's hot in here. Anyways, whatever. Okay, so let's talk about these. I know that this is boring, and I know this kind of sucks a little bit, but we have to really understand what these forces mean and what causes them in order for us to move on. If we move on without understanding these forces, woo, we're going to have a bad time. Okay, so we really have to get an idea of what's going on. This is what F applied typically is called. F applied, F-A-P-P, whatever. It is what it is, I know. It's the applied force from a person or an object. Sometimes we'll call it FA on B. So like for example, let's say there's a ball and it strikes another ball. This is A and this is B. Would you agree? B is going to feel a force when A hits it, right? So we could say FA on B, that's an applied force. Or we could say FB on A. Some physics teachers really shorten this and they write FAB. What does FAB mean? A on B. So who's feeling the force here, A or B? It's B. B is feeling the force because A is applying a force onto B. B is feeling the force here. So it's we'll talk about it. It'll be okay. We'll get used to it. Okay, so that's an applied force. FF. It's the force of friction on an object. The direction of FF always opposes what? Let's say here I'm going to take my hole puncher and I'm going to put it on the whiteboard, okay? Boom, it's on the whiteboard. And I'm going to push it up. Okay, I'm pushing it up. Where's friction acting? In what direction is friction acting?
Down.
It's down, right? If I try and push it to the right, where's friction acting? To the left. If I try and push it to the left, friction is acting to the right. So what direction does friction always oppose? It's the motion of the object. So it always opposes the motion or the intended motion of the object. I'm going to switch to a new digital page. So here I am killing digital trees. FG, that's the force of gravity. Or force due to gravity, whatever. What is, where does the force of gravity always point?
Towards the center, the largest mass.
Okay. Because I was going to say, does it always point down?
No.
No, because if this is the Earth, and if Mr. Walton's standing on the Earth in Australia, Antarctica, whatever, okay? So where's gravity pointing? It's technically up, right? But it's pointing towards the center of the largest massive object, celestial body, right? So as long as we're cool with that, typically it points down. Because most of the time we're talking about small, tiny objects on or close to the surface of the Earth. The force of gravity can be calculated using the following equation. And it's this, again, this is on your equation sheet. So how can we get the force of gravity? Well, this is force of gravity, but this is between two massive objects. Not too massive, any two objects. But we're going to be using this when we talk about, like, here's the Earth and here's the Moon, and do they have a force of gravity between them? So this is talking about, like, that kind of force of gravity. So here we go. Here's an equation that has force of gravity in it. So what's force of gravity equal to? G times M, right? Or mg. That's the way people typically write it. It's mass times g. What's g again? G is not gravity. Whoa, it's acceleration due to gravity. It's an acceleration. Woo! So this is typically as mass. G is acceleration due to gravity. Oh, okay. Hey, as long as we're on the surface of the Earth, what can we assume G is? Yeah, so typically negative 9.81. Why negative? Because things accelerate down in our traditional frame of reference, right? Okay. So hopefully that makes sense. That force of gravity will be negative as well. It'll always point down as long as we're doing like really traditional perspectives. Okay, this is the one that kind of messes people up. This is the normal force applied on an object when it is in contact with a surface. It's a special type of applied force, but it's an applied force when an object is in contact with the surface. I'm curious, okay, I've got my hole puncher. Where is the normal force acting? In what direction is the normal force acting on this hole puncher right now? It's acting up. Okay, would you agree? Because the surface is pushing back up on the object. The object is pushing down because gravity is pulling it down. The surface is resisting, so it's pushing back up on it. Okay, I'm curious. This thing is in contact with a surface. Where is the normal force applied on this surface? It is out of the whiteboard at you. Does that make sense? Okay. Now, we're going to take a surface. Now, where is it pointing? It's kind of up at an angle. So what can you say? Where is the normal force always pointing? It's perpendicular to the surface, right? The surface is left and right, then it's going to be at a 90-degree angle to that surface. So Fn always points perpendicular to the surface it's sitting on. Okay, so what we're going to do is we're going to really simplify diagrams of objects by using a free body diagram. A free body diagram is just a really simplified picture of what is happening to this thing. What are all the forces that are acting on this object? Typically, we draw it as like a box with a dot in the middle, and then we draw forces coming out of the dot. A lot of the time, I just use a dot. Okay, so if you see a textbook doing this, that's awesome, that's great. I do it the not proper way. I typically use just like a dot, okay? So let's imagine a box sitting on a ramp and it's stationary. So we're going to draw a picture, but then we're going to draw a free body diagram for that object. Here's a ramp. You place a box on the ramp in the exact same way that I'm placing this hole puncher on this thing, right? Okay? Right here, right now, is it moving? No, so it's totally stationary on the ramp. Let's draw it. This is pretty complex, but I want us to kind of understand what's going on. So there's a box sitting on the ramp, and it's not moving. So we're going to draw a free body diagram for this thing. Here's the free body diagram for this thing. So I'm going to draw a dot. People usually draw a box with a dot, and that's fine. You draw a dot. Are there any forces acting on this object right now?
Force gravity.
There's a force of gravity, right? Would you agree the force of gravity is pointing down here, right? So our proper free body diagram should look like this. It's a dot, and the arrow should come out of the dot. And we're going to name this thing FG. Now, are there any other forces acting on this thing? Yeah, this thing, would you agree, if I put a bunch of, this is going to sound really dumb, but if I put a bunch of like oil on this surface, and then I did this, would it be able to slide down the surface? Yeah, because I'm reducing the friction between the two things, right? So, in what direction is friction pointing? Yeah, where does the object want to go? Down the ramp. So friction has to oppose the motion of the object. So where is friction going to point? It's going to point up the ramp, parallel to the surface that it's sitting on, right? So here's the force of friction. Now, are there any other forces acting on this object? There's a normal force. It's an object sitting on a surface. And in what direction is this normal force pointing? It's perpendicular to the surface that it's sitting on. So perpendicular to the surface that it's sitting on. Fn. Because it's stationary, what can you say about all of these forces? If you add up all the forces, what is it going to add up to be? 0. Is that hole puncher, is it accelerating right now? No. That means all the forces that are adding, when we add up all these forces, they add up to be 0. And that's good. That's really important. Good. Okay, that's awesome. Yeah, I'm going to go to oh, no, I'm not going to go to oop. Forgot about one. Lots of people, I think the physics community typically writes it as FT, the force of tension. I had a really old school physics teacher when I was in high school, and he wanted us to write it as just T, capital T for tension. You can do either one. In a lot of my answer keys, you'll see capital T meaning tension. I'll try my best to use FT. Does that make sense? I'll try my best, but if you ever see T, that's like the old habits kicking in for me, okay? So tension, where would you see tension? What is tension? What kind of a force, when would you see tension? Have you ever heard of that before? Yeah. I see people miming it. Yes. So it's the pulling force of a rope or a chain or a cable or anything like that. It's always in the direction of the rope. So let's imagine a scenario where Mr. Walton wants to lift up something really, 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 really heavy. Okay, he wants to lift up something incredibly heavy. So here's the ground. Here's a box sitting on the ground. And Mr. Walton's in a shop, okay, so there's a roof over our heads or something like that. How can Mr. Walton lift up this incredibly heavy object? It's way too big for me personally to like lift it up. So what I could do is I could put a pulley above it, right? And then I could take Mr. Walton or whatever, right? I could have a rope and it would wrap around the pulley and attach itself to this object. And then I could take Mr. Walton's 2007 Honda Odyssey. Whoa, right? And could I pull that extremely heavy object? Could I lift it up using a rope that was sufficiently strong and a pulley? So Mr. Walton is applying a force onto the rope. So I'm putting the rope in tension. So the force of tension over here, would you agree, if I pull on a rope, the rope kind of pulls back on me. Does that make sense? Yeah, okay. So the rope, the force of tension, well, I should draw that differently, right? The actual force of tension is going this way on the car. The rope is pulling back on the car. But here, the object also feels that force of tension. What direction is the force of tension pointing? It's pointing up. And what can you say about this force of tension and that force of tension? They're equal to each other because the rope is the one transferring the tension from one side to the other. Yeah.
Would you divide it by like the number of pulleys? Like if there was 2.
Yeah, we're not going to talk about pulley systems, but yes, you would. There's mechanical advantage in using multiple pulleys. Yes, there is. Yeah. But we're only ever going to talk about a single rope over a single pulley. So this force of tension is that force of tension. That's awesome. Okay, cool. So now we have enough information for us to kind of really start to analyze like forces in general. So let's go back to our analysis of Mr. Walton in space or you in space or whatever, that kind of thing, okay? Okay, so let's think about this for a second. Mr. Walton is in space, okay, in a spacesuit, but Mr. Walton was a little bit of an idiot, and he brought his snake.
Oh no.
In space.
No, of course.
Okay,
No,
but he's in a space.
Oh, okay.
A space
okay.
suit. Okay, so he's good to go. He's totally fine. So Cornflakes is in a snake suit, and then Mr. Walton is in a human space suit. That's a weird thing to say. So let's think about this for a second. Well, the spaceship, they throw a tether my way. I attach the tether to me. They have to apply force to accelerate me towards the spaceship. But they have to do the same thing to Cornflakes. So they throw out a tether, right? I'm not close enough to Cornflakes. I can't reach him. So they have to throw out a tether. Cornflakes attaches the tether to himself, okay? And then they have to apply a force, and they have to try and accelerate Cornflakes to the spaceship as well. So they're trying to accelerate me, and they're trying to accelerate Cornflakes. What can you say about the force required to accelerate me versus the force required to accelerate Cornflakes? If we wanted to get to the space station at the same time, if we wanted to have the same rate of acceleration, what could you say about the force required to pull me and the force required to pull Cornflakes? What could you say? Would we require the same force?
No.
No. Who requires a greater force? Why?
More mass?
Because I'm what?
More mass?
Am I more massive than Cornflakes? Yes, I am. Absolutely, right? 100% I'm more massive than Cornflakes is. Okay, so this is This is something called Newton's first law, and I forgot I was trying to clean up a lab, and I apologize, but I was supposed to do a video right now, so just have mercy on me.
Around the Earth.
Okay. Hey, Austin, lights off at the back of the class, please.
Mark Vande Hei on the International Space Station to find out.
Newton's first law of motion says an object at rest tends to stay at rest unless acted on by an outside force.
Okay, would you agree? Would you agree he's got like a weight here, like a medicine ball or inflatable ball, I don't know, I can't remember. Okay, and so even though he's not holding it up or anything like that, that object is at rest right now. Okay, cool. So the only way for this object to not be at rest anymore, the only way to give it some motion is to apply a force on it, right? So what we're saying is an object at rest is going to stay at rest unless acted on by an external force, by an outside force. So some outside force has to do this. This is like if Mr. Walton was here, right? Could I pull on myself to get myself to move when I'm out in space? If I'm out in space, could I just grab part of my body and be like, okay, move this way? No, that's an internal force, right? So me pulling on that way is like me pulling on that way, and they cancel out. So something else has to push onto this object. Okay, I'm going to start the video again.
Also, an object in motion tends to stay in motion unless acted on by an outside force, like my finger.
Let's look at this from another angle. Over time, the International Space Station slows down from experiencing a very small amount of drag, or force, from a tiny amount of atomic oxygen in space. This is like the force you feel from the air if you stick your hand out of a moving car. Because of this, the space station does what we call a reboost. A reboost uses rocket engines to put a force on the space station. This allows it to speed up just a little to remain in orbit around the Earth.
Okay, are we okay with that? So that is something called Newton's first law, and it has to do with the idea of inertia. Okay, Austin, turn the lights on, please. I'm sorry, there's so many terms. I apologize. I know that this sucks, but it's the beginning of a new unit, and we're learning the fundamentals of a totally different type of physics. So we just gotta plow through. Okay, so inertia is a property of matter, but inertia is the ability of an object to resist changes in velocity. Okay, so let's think about this for a second. I want to stop some objects. I want to either speed them up or slow them down. So I have Mr. Walton's minivan. Do you think if we put Mr. Walton's minivan in neutral, what that means is the gears are not engaged with each other? If we put Mr. Walton's minivan in neutral, do you think Mr. Walton is strong enough to be able to push Mr. Walton's minivan? So Mr. Walton's minivan is pretty darn heavy, right? It's like over a metric ton. It's very, very heavy. It's got a lot of inertia, so it's going to create, or it's going to take a lot of force to cause it to change velocity. But Mr. Walton's strong enough, I can push a minivan. As long as it's in neutral, That's fine, I can do that. But let's take a really massive semi-tractor trailer. And let's say that it's in neutral, so the gears are not engaged. Is Mr. Walton strong enough to be able to push a humongous tractor trailer? No. It's got greater inertia. It needs a larger force in order for us to be able to change its velocity. So all I'm trying to say is that the inertia of an object is related, or proportional, sorry, it's proportional to the mass of the object. It's easy for me to stop a baseball traveling at 100 miles an hour. That's totally fine. I can catch a baseball going 100 miles an hour. But if somebody launched a motorcycle at me going 100 miles an hour, it's going to be a lot more difficult for me to change its velocity. That's the idea of inertia. Inertia, the more massive it is, the larger a force is required to be able to change its velocity. So, I'm sorry, we got to write some stuff down. I'm so sorry. Newton's first law.
Oh, Dad. No, Dad. What's that mean, big nose?
Objects at rest tend to stay at rest unless acted on by an external force. That's not how you spell external. And then it's the exact same statement, but how could we switch up that same statement? Yeah. Objects in motion, so I'm just going to say objects in motion tend to stay in motion unless acted on by an external force. It's the exact same statement, we're just switching up rest and motion. If you want to get something to move, you've got to apply force. The larger it is, the larger force is required to get it to move. Okay. Whew. So let's actually start asking ourselves like what's going on. So for example, here, stuck behind the smartboard. Ooh, there we go. So here's a pulley, but we're not going to actually use it as a pulley. This is just an object that's hanging by a rope or hanging by a string. So Mr. Walton has this object. It's attached to a string, which is attached to something else. Let's draw a picture of this thing. So we're actually going to start kind of analyzing situations. A 100-gram mass is attached. That's not even spelled attached. To a string hanging from the roof, from the ceiling. How do you spell ceiling? Is it I before E except after C?
Yeah.
Ceiling. Perfect. So we could draw a picture of this, sure, but let's actually draw a free body diagram. What are all of the forces acting on this thing right now?
Gravity.
So, okay, so we've got an object, a dot. Gravity is absolutely pulling on it, so that's the force of gravity. There's another force acting on this object. What's the other force? Tension. Here, I'm interested, how large should the tension arrow be? It should be equal in size to the force of gravity. Why? How do you know that to be true? Because this thing, is it accelerating right now? Is its velocity changing? No. So it's at rest, sure, but its velocity isn't changing, so that means all of the forces on this object are equal to each other. Ft, you can do it, Mr. Walton. There we go, perfect. What I want to know is, what is the force of tension in the system? Do you know what the force of tension is? Ooh. Well, we don't know what force of tension is, but what do we know? We know the force of gravity. You absolutely know the force of gravity. So, what I'm going to do, I'm just going to describe this situation a little bit. Since the mass is not changing its velocity, should that be an apostrophe on its? It's possessive, but I don't think you're allowed to. Are you? It's whatever. Damn you, English. Since the mass is not changing its velocity, then the net force of the object is 0. So all forces cancel out, or they add up to be 0. So I'm going to ask 2 questions. A, what's the weight of the object? What is the weight of the object? And this is where physics is a little bit of a jerk. Because we use the terms mass and weight totally interchangeably in like regular common vocabulary, but they're not the same, okay? I want to be really clear. Let's say you're out in space. You're out in space, right? Mr. Walton's out in space, okay? And we put a scale underneath Mr. Walton that could read his weight, right? Just like a bathroom scale that you would use in the bathroom, check your weight or whatever, okay? So what is Mr. Walton's weight going to be if we put a scale underneath him?
Students that are needing photo retakes with the last names K through to M can now go to the main staff room. Thank you.
Ryden, what's the scale going to read? 0. Am I applying a force on that scale? No. I'm not applying any force on the scale at all. So my weight is 0. But do I still have mass?
Yes.
Do I still have inertia?
Yes.
Yeah. So you can have mass, but you can have no weight as long as you're in a situation where the force of gravity is essentially 0. Okay? So what is the conclusion here? Well, when we say weight, what are we really saying? In a physics context, your weight is the force that gravity is pulling or pushing on you. Always pull. So this is what I'm asking for. I'm asking for your weight. Weight is force of gravity. Hey, well, what's force of gravity? Nope, not in this case. Is this pulley, is gravity pulling down on it? Yeah, it is, right? Now, if I put a scale under it, it's going to read 0 because there's something pulling back up on it, right? But if I took the pulley off of this and put it on a scale, would it read some value?
Yep.
Yeah, it would, absolutely. So what we want to know is, what is the force of gravity? That's what we mean by weight. Hey, what's force of gravity equal to? I already told you. It's mass times acceleration due to gravity.
So negative 0.9.
Okay, so what's the mass of this thing? It's 100 grams. So this is 100 grams, but how do we turn grams into kilograms? It's the first time we've done this so far this semester.
Divide.
Do you know how many grams and kilograms are equal to each other? Hey, what's bigger, 1 gram or 1 kilogram?
1 kilogram.
Okay, so I'm just gonna write that down. Whoop, come on, you can do this. There we go. So off to the side,
Kilo.
1 kilogram is bigger than 1 gram. So how many grams are in a kilogram? 1,000 grams. We want to turn grams into kilograms. Should we multiply by 1,000 or divide by 1,000? Divide by 1,000. Does that make sense? How do you turn grams into kilograms? Well, you got to go from 1,000 to 1. How do you turn 1,000 to 1? Do you multiply or do you divide? You divide. Divide by 1,000. Okay, so our mass is not 100 grams, it's 0.1 kilograms. And our acceleration due to gravity is negative 9.81 meters per second squared. What's 0.1 times negative 9.8? 0.981. And then what are we going to write here? It's a force, so what unit should it be in? Newtons. Fantastic. Okay, so all that means is that gravity is pulling down, right? This negative just means down. That's all it means. With a force of 0.981 newtons. Is this a vector? Yes, it's got a direction and it's got a magnitude. Fantastic. Okay. Now what I want to know is, what is the force of tension in the rope? And this is where, for the first time, we're actually going to think about net force as what it should be, okay? So what is the force of tension in the rope? Well, it's asking about another force, and maybe we can't immediately answer it, right? We probably should know, but even if we didn't know, that's totally fine. What I'm going to do is I'm going to write out an F net. And I want you to wake yourself up if you're falling asleep. I want you to actually listen to this, okay? Caden, you doing okay? You good? Yeah, I know, I'm sorry. It's hot in here. We've been yapping on for a really long time. What I'm going to do is, what direction is everything pointing? Is everything in the X, is it in the Y, or is it in a combination of X and Y? Everything's in the Y direction, okay? So we only care about the Y direction right now. The F net is what you get when you add up all of the forces in the Y direction. This is F net in the Y direction. What I'm going to do is I'm going to take all the positive forces and then I'm going to subtract all of the negative direction forces. And that way we don't have to worry about positives and negatives right now. So which forces are acting in either a positive or a negative direction? Here we've got Ft. Is that in a positive or a negative direction? That's, yeah. So the force of tension is in a positive direction, right? Up should probably be positive. Could you define it to be negative?
Yeah.
Yes, you could, totally. There are situations where that's helpful. And then, so force of gravity, we're going to define to be in a negative direction. So what we're going to do, your physics textbook is going to go this. Okay, don't write this down. They're going to say Ft plus Fg, but what do we know about Fg? It's negative. So the way we're going to write it, we're not going to write Ft plus Fg, we're going to write Ft minus Fg, knowing that the negative is already taken into account. So we're going to keep going with this, okay? What do we know the net force is on this thing? What do we know for sure the net force is? It's 0. So we're gonna cancel it out. If you're not accelerating, that means your net force is 0. So we're gonna simplify this a little bit. 0 equals Ft minus Fg. What are we looking for in this case again? Trying to find the force of tension. So how do we get the force of tension? What do we got to do in order to get force of tension by itself? Add Fg to both sides. So we're going to get force of tension is equal to force of gravity. So we know that, but that was the conclusion we already came to, right? We already knew that they should have been equal to each other. So force of tension, what should it be? Should it be positive or negative 0.981? So we're going to say positive 0.981 newtons. We're using the context. We know Ft is in a positive direction, so you just put positive there. And we know Fg is negative, but we already took that into account. We'll get used to this. Trust me, it'll be okay. Okay, perfect. So positive 0.981 or 0.981, no problem. A 9.1 kilogram mass is sitting on a scale. A student applies a downward force of 15 newtons to the mass. A, draw a free body diagram. Well, what the hell is a free body diagram? It's a dot or a dot within a box, depending on who's your teacher. And we're going to draw all of the forces acting on this thing. So let's imagine that we had a box, it was sitting on the counter, right? And then somebody takes a force and pushes down on the box, okay? Is it going to accelerate somewhere? Is it going to start changing its velocity? No, right? You're pushing down on this box, but it's pushing down on the counter. So is it going to start moving somewhere? No. So what do you know the net force is on this box? 0. The net force is still 0. We're just complicating it a little bit, okay? What are all the forces acting on that box? The box is just sitting there. What are all the forces acting on the box?
Force normal?
Is there a normal force?
Yes.
Is the box sitting on a surface?
Yes.
Yeah, it is, right? Absolutely. Mass is sitting on a scale, so it's sitting on a surface, 100%. There is a normal force. Totally, there's a normal force. What else? What other kind of forces is there? Quick.
Gravity.
Yeah, is there a force of gravity?
Yeah.
Yes, it's pulling down. I don't really care about the size of the arrows right now, because we don't know what the arrows' sizes should be. So don't worry about the size of the arrows right now. Okay, we're going to say that this is the force of gravity. Okay, and then is there an applied force? You're pushing on it. What direction are you pushing? Down. So there should be another arrow going down. It's okay to write it, to draw it kind of off to the side. That's totally fine. I'm not trying to make it equal to Fg. I'm just drawing another arrow. Should I make it a very specific size? Yes, but I don't know how big it is. So what is the downward force? The downward force of 15 newtons, right? So I'm going to go F applied. Good. So that's our free body diagram. There's one positive force and two negative forces acting on this thing. B. What is the net force acting on this object? What's the net force acting on this object? Is it accelerating? Is its velocity changing? No. So because no change in velocity equals F net of 0. Its velocity is not changing. This is why I never open the windows or open the blinds. Okay, calculate the normal force. This is the very last thing that we're going to do today. This is the very last thing. It'll be okay. Don't worry about it. Calculate the normal force. I want to be really clear to you. Anytime you draw a free body diagram, you should also be able to write out an F net equation. That's going to be really key, and we're going to remind ourselves on that after your 5-day weekend on Tuesday. Anytime you draw a free body diagram, you should be able to write out an F net. So let's do that. It's saying calculate this force, so let's just jump straight into F net. What direction is this in the X or in the Y? Yeah, so it's in the Y direction. F net equals, I don't know why I said F net colon, F net equals. What are all the forces acting on this thing? Let's do all the positive forces, and then let's subtract all the negative forces. So what are the positive forces here? F normal, right? Fn, okay, is that the only positive force?
Yep.
Okay, so now I'm going to go minus, what are some negative forces? Fg is a negative force, and then I'm also going to go minus, because it's a negative force, what's the other negative force? F applied. Let's break this down a little bit further. Let's kind of split this up a little bit. What do you know F net is? It's 0. Do you know what the normal force is?
Yeah.
No. Do you know what the force of gravity is? Yeah, you do. What's the force of gravity? It's not negative 9.81. Okay, what is Fg equal to? Off to the side, we could do this. Fg is equal to what? What's Fg equal to? Mass times acceleration due to gravity. It's equal to mg. Fg equals mg. So, what I'm going to do is I'm going to leave it up to you. Could you calculate what Fg is off on the side of your page?
Yeah.
Yes, you could. Easily you could do that. Just take the mass and times it by acceleration due to gravity. But this time don't use negative, because we already know that we're using the negative. Just go mass times 9.81. What I'm going to do is I'm going to go Fg is really mg. I'm substituting in what it's equal to. So instead of writing Fg, I'm writing mg in its place. And then instead of writing F applied, what could I write?
15.
Yeah, do you know what the applied force is? Yeah. It's 15 newtons. Okay. What are you interested in? What's the thing that you want?
The thing.
Could you rearrange for Fm?
Yes.
Yes, you easily could. What do you got to do? to move mg over to the other side? You gotta add mg to both sides. Add mg. Add mg. What do you gotta do to the 15? You gotta add 15 newtons. You gotta add 15 newtons. So really, the normal force is equal to mg plus 15 newtons. So either figure out what the force of gravity is off to the side, that's totally fine, or figure it out right now. What's the mass of the object? 9.1 kilograms. What's acceleration due to gravity? 9.81 meters per second squared, plus 15 newtons. Grab your calculator. You go 9.1 times 9.81 plus 50. 104.271 newtons. So this is what the normal force is on the object. We got to round this to a certain number of significant digits. How many significant digits? We want 2. Yeah, we want 2 significant digits. So what's this going to be? 1.0 times 10 to the 2 newtons. And what direction should it be pointing?
Down. Wait, no, up.
Where's the normal force pointing? It's pointing up. So we could go up, or we could say positive. The absolute 100% most important thing to take away from today is when you draw a free body diagram, this is literally an equation, right? In the y direction, the net force acting on an object is all the positives minus all the negatives. Are we okay with that? So we're going to continue with this. It'll be okay.